Go.
I can explain what a limit is. I can find limits by using the properties of limits.
That is one of the most eloquently read learning targets I've ever heard, said no one ever. Okay? Yeah, I can explain what a limit is, and I can find limits by using the properties of set limits. All right? So let's start doing some calculus, right? So here we go. You're going to see this notation a lot until we get to derivatives. But this will build derivatives. This course, half of it is derivatives. The other half is anti-derivatives. It's going backward with derivatives. We're going to go forward with derivatives and backward. This will get us into derivatives. Okay? This is the limits. Okay? LIM, you see me write that when we did the instantaneous time. Okay? The limits of some function. Okay? As the x value approaches some number or value, the function will return a value. They call it L. They just use not. It's easier when we start using it and putting numbers in there. It starts making sense. Okay, this is just notation. So by definition, for your given function f of x, as the x value approaches c, whatever c is in our notation, it's a number will be in for c. The y value of that function will approach whatever the number L is. Okay. Put in a number in the function, and you get out a number, right? Your x is your input or independent variable, right? You put in that number, and you do something to it. Maybe you square it and multiply it by 9, but the bell one probably just did was. All right? And whatever that outputs, that's what your L is going to be. Okay? So I'll read that again. For your given function f of x, as the x value approaches c, the y value of that function will approach L. Now, I can put numbers in here. We can read them with numbers, and if that's easier, it makes more sense. But this is how you're going to see it in college textbooks and things, and you got to kind of make sense of it. So, for example, let's say f of x equals 3 times x. That's my function, 3 times x. So as x, we'll put a number here. Someone pick a number between 1 through 9. I heard 7 first, sorry. If this was 7, as x approaches 7, what is the overall value of the function? 21 is 3 times 7. So this will be 21.
You want to write that?
No, I'm just showing it to you. I mean, if you want to write it off to the side, you can, but I just want to give you an example of numbers. So how do we read that? How do I say that? I actually say that, I say the limit of f of x as x approaches c is L. So in our case with the numbers, if I were to put a 7 here and a 21 there, I would say the limit of f of x as x approaches 7 is 21. Okay? 21.
Yeah.
And there you go. So it's not too crazy. This is more the definition. It's more important that you know kind of how to say it, because once we get numbers in there, you'll understand it a little bit better at this point. And once you start using it, we'll go over some of that. We will go over some of that. It's a very good question. We'll get there. So, all right. Do we need to go back? Are people still writing? Mm-hmm. You couldn't read through the green, or? I gotcha. The limit of f of x as x approaches c is L. All right? All right. So now we have, okay, definitions of a limit. Now, for A here, we have a function. Our function f of x is x squared minus 1 over x minus 1, and they give us a graph of that. Okay. For B, we have a piecewise function. We have the same thing, x squared minus 1 over x minus 1, but for this piecewise function, they actually give us a value. Okay. When x is 1, Okay, when x is 1, our function is going to be equal to 1. See here, there's a hole there. There's no value when x is 1. When my x is 1, I don't get a value for y. Okay, here now, they're saying, okay, when x is 1, I get a value. My y value is 1. That's what that is. And for C, they just give us the line x plus 1. They look very similar. Yes?
One of them is closed circle, one of them is open. Does that mean anything?
Not for limits. And I will explain to you in a second. Now, what a limit is that when I approach that x value, when they give me an x value, okay, I'm going to approach that x value from both the left, I'm facing the other way, so I got to, and the right side. And as I follow the graph, it's a curve or even a straight line, like in this case. If they both point to the same value, if they are both approaching the same number, that number is the limit. Let me explain. See this down here? The limit of f of x as x approaches 1 is equal to the limit of g of x as x approaches 1. And that is equal to the limit of h of x as x approaches 1. They are all equal to 2. And let me explain that to you, because some of these graphs are like, but there's a hole in that graph. Let me explain. Okay, so first of all, you'll notice that the limit is as x approaches 1 for all of these. Okay? So let's look where x is 1. It's right here where x is 1. Right here is where x is 1. Right here is where x is 1. Now, if I follow my graph, okay, this is my graph right here. There's a hole there, and there's a hole right there. Now, if I were to follow this line coming from the right side, all right, I'm following this line as I come down the right side, as I come to this x equals 1 line. You see what I'm saying? As I approach the 1 on the x-axis from the right, and if I approach it from the left, they both point to what number on the y value?
2.
So that's why the limit is 2, because they both approach the same number. But there's no actual value. When x is 1, that's undefined, isn't it? Because if I put a 1 in here, 1 minus 1 is 0. A limit doesn't want the exact value at that spot. I don't want the value at 1. Here, it's undefined. I just want to know what it looks like it's approaching from both sides. It should be the same number. It happens that both of these, when I approach this way and I approach this way, they both approach this, even if it's a hole, but they both approach that same hole, which is where y is equal to 2. And that's why this is equal to 2. Let's look at the next graph. Same thing. As I come from the right side, so x equals 1. I'll do this in purple. This is my x equals 1, right? If I approach from the right side, and as I approach from the left side, they both approach this spot right here, which is where y is equal to 2. Big deal. When x is 1, that actually gives me a coordinate here. The graph doesn't approach that from the left and the right side. It still looks like it's approaching 2. So it's 2. What about the last one? The same deal. All right, here's where x is equal to 1. Anytime our graph crosses that point, that's where we're approaching. So as I approach it from the right, as I approach it from the left, it approaches a spot right here, and I think it's 2 as well. They're all 3 the same. Given those 3 situations, there's a hole at x equals 1, there's a hole, and there's a point somewhere else where x is equal to 1, and here you actually have the value of x equals 1 at 2. They all 3 lines approach. As you get closer and closer and closer and closer to x equals 1, it looks like y is 2. Okay? Yeah, now, not to get confused, what's the value of the function? If I put a 1 into the function, forget the limits, it's undefined because it doesn't exist. It's a whole. The limit exists, the value does not exist. No. The limit is where it points to. It looks like it's pointing to 2, both sides, so it's 2. But what's the actual value? It's undefined. What about this one? The limit for the middle now. The limit is 2, but what's the actual value of f of 1 in? I think this is the point here where y would be 1. The limit is still 2. What about the third one? The limit is 2 because it's where it's pointing, but what's the actual value? Well, this actually has a point here, so it would still be 2. So limits and actual values, sometimes they can be the same, like they are here. Sometimes they can be 2 different things, which they are here. Sometimes the limit can exist, but the point cannot. The limit is just what it looks like. It's as you get closer and closer and closer and closer, what does it look like it's pointing? It's almost like predicting. You want to think of it that way. Everybody likes prediction. Okay? Mm-hmm. Now, properties of limits. Properties of limits. If I take the limit, actually, I'll just the limit of any constant k is that constant. So we just look at some function, taking the limit of like x squared minus 1 over x minus 1. That's has variables in it. It's a function, whatever. But what if I said my equation was just 5? There's no x in it. Find the limit as your function is equal to 5. Well, then it is 5. It's that number. That's all that's telling you. Okay, from the previous problems here, we had these crazy functions, didn't we? We had this here where there's x's and you put in an x and you're going to put it in your fraction. Well, what this is telling you is, what if your function, what if this wasn't x squared minus 1 over x minus 1? What if it wasn't that? What if it was just the number 5? The limit of 5 as x, yeah, I'm writing that like it's a fraction. Okay, the limit, I'll write it up here so I have more space. The limit of 5 as x approaches anything. It doesn't matter what it approaches. If it's just a number without a variable, it would always be that number. Right? What about this? Now, the limit of the, I think it's called the identity function. That means like y equals x. Man, you need help. Okay? The limit of the identity function x is whatever c is. It's whatever x is equal to. For example, okay, the limit of the identity function x is c. So instead of having a 5 here, or having this fraction here that I crossed out, if I have the limits of x as x approaches 3, guess what? Right? If y equals 3, what happens? Yeah. If y equals x, what happens if I throw a 3 in for x? Wouldn't y be 3? What happens if I throw a 5 in for x? Wouldn't y be 5? Yeah. What happens if I throw a pi in for x? Wouldn't it be 5? So whatever value this is, this has got to be. All right? It's the simple stuff. It's worded weird and.
So that's the y.
In this case, yes. In this case, yes. Or instead of y, they can say f of x instead of y. All right?
Yeah.
Not crazy.
Nope.
This is where we lose it, children. This is where we lose it, children. Children! You know what? These are so basic, these rules, it's crazy. I mean, this limit, this x approaches c, and that, it looks intimidating, but it really is not. It really is not. So, let's do this. Are you ready?
Are you ready?
All right. The sum rule. This tells me, kind of like log. Remember our log rules? How you break things up, put things together, right? We got a dozer. We got a dozer. All right. If I'm taking the limit, pay attention. If I'm taking the limit of 2 separate functions, okay? If I'm adding these 2 functions, and I'm taking the limit of the whole thing, I can basically take the limit of the first one and add that to the limit of the second one. I can take the limits individually, and I still add them together. See what I'm saying? And we'll do these so that you kind of have a better grip on it. All right? Oh, plenty of time about to go into 24.
I don't understand those things on the bottom.
Yeah, we're going to go over all that. Don't worry. I've explained them, but until you see numbers and you start using them with numbers in there, it's going to become easier. All right? What do you think is going to happen if I take the limit of two functions and I'm subtracting those two functions? Don't think long. Stop it. Look what I did here with the first one. If I'm taking the limits of this expression, yeah, I can just. You see how I took the limit of the first one, and then I still added that to the limit of the second one? Well, I did the same thing. We'll just keep a minus sign between. If you have a big complicated function that's separated with pluses and minuses, you can just take the limit of each of those terms separated by pluses and minuses and still add and subtract them instead of trying to take the limit of this whole god-awful thing. Yeah, but you know what? When you get a polynomial and start taking derivatives of it, it's just becomes it's so easy. You guys are gonna get so pissed that I even showed you this first. Yeah. Okay, so what do you think's gonna happen if I multiply? Wrong. I divide. This is. I'm just kidding. It's no. You're still multiplying. You're still multiplying. I know. I mess with you guys. So if I'm taking the limit of two functions that are multiplied together, why don't I take the limit of each of those individually, which will get rid of them because I'm done, and then multiply? Yeah. Yeah, man. Okay. The constant multiple rule. This k here stands for some constants. I can put the number 3 there, or 8. If I multiply 8 times some function, well, what I can do is I can take that constant out, take the limit of just the function, and then after I get the limit of the function, then multiply it by my 8, or whatever constant it is. That's a really useful one. That can make life easier sometimes. All right? If there's a constant in there, I can just take that constant out, all right, if it's a lead coefficient or whatever, and then find the limit of my function, then multiply the constant back in. All right. What do you think we're going to do with the next one? It's the quotient rule. It is. I'm going to take the limit of the top and divide it by the limit of the bottom, and that's exactly what we're going to do here. The limit of the numerator over the limit of the denominator. So much easier, children. So much easier. Question. Question. What do you think's underneath that next box? Well, no, it's right next to our quotient rule. But what do you? Whenever we have fractions, just the one thing we just got to make sure. Bam! The bottom cannot be equal to 0 here. So it's a general rule of fractions. The bottom can't be 0, otherwise we rip a hole in space and time, the fabric, and the black hole has started. And hopefully it's not in this classroom because we'd be all screwed. All right. And last but not least, a weird one. If I'm taking the limits, okay, of this, let me extend this. If I'm taking the limit of this whole thing, I can take the limits of just the function and apply the exponent to it afterward. All right? So I can take the limit. Notice where the brackets are of the expression I just uncovered. It includes the limit in there, but it does not include the exponent. It includes the limit in the function, but not the exponent. I can do the exponent afterward. I wouldn't even be. We're going to start doing some of these things, and they're going to be easier. Trust me. It's going to be cray. And of course, because we have a fraction in for the exponent, what's my one rule I got to make sure? S cannot equal 0 in this case. S cannot equal 0 in this case. So let's do an example. We're going to use most of our rules from that list we just took, and we're going to solve it step by step. And then afterward, we're going to show you another way, and you're going to do it this way. But I was proving to you why the other way works. All right? So now, what am I going to do? First off, I've got a limit of a polynomial here. So what should I do? Yeah, I'm going to break it out. I'm going to use the addition. What was it? I don't even know what it was. The addition and subtraction rule. Yeah, that's what yeah. So I'm going to take the limit as x approaches c of x cubed plus the limit as x approaches c of 4x squared minus the limit as x approaches c of -3. That's the first thing. I'm going to break those up into pluses and minuses. So what about the first one here? The limit of x cubed as x approaches c. Yes. You should write it, but it depends on your work. Relax, be patient. Let's wait. Let's walk before we start running. Because right now there's a wheel of cheese rolling down a hill, and you guys all want to run as fast as you can down the hill. Some of you are going to scorpion. Some of you are going to scorpion. Now wait. What can I do here? What rule can I do maybe here? The exponent rule. The exponent rule. So now I can say the limit of x as x approaches c, and then I could cube that whole thing. Right now, remember the first two rules I had before we did all those other rules? The one with the k for the constant and the identity rule. What do I have here? This is the identity, right? What is that? What can I do for the identity?
I don't know.
What do I put in there?
X is c.
Yeah, whatever x equals, I can just put it right in there. So now I have c cubed. So that's c cubed, the first one. Okay. Okay. Good. Now, there are two things that I could do to this one right here. So I want to look here. What can I do? I could pop the exponent out. Okay, so I'm going to do this, and I still got the plus here, right? It's the limit as x approaches c. And I'm going to pop out the 2. But what else can I pop out?
How about the 4?
The 4 is the constant that I can pull out and then take the limit out the inside and multiply it back in. So I'm going to pop the 4 out and the 2 out, and I just have my x left. Oh my God, that's another identity. What happens? What happens now? What's the limit as x approaches c of x? The c just goes after the x. That is c right now. In these brackets, that is equal to c. I multiply it times 4, and I square it. So yes, I have 4c squared. Look at the last one. Yeah, that's the constant one, isn't it? There is no x to throw that c into, so that is just... This is the limit of that whole big thing, because you broke it down and looked at it individually. Take a look at what we started with in parentheses. This is where you guys want to start throwing pens and calculators at me. Let's look at what we started with and what we ended with. What do you notice? What do we just do? We just plug the c in for the x's. So as x approaches c, I can just put my c in for that x and my c in for this x. Yeah, stop snapping your teeth. No, now you know how it works. So let's use substitution for this one. Let's not use the rules. What would I do here? What would I do here? I'm going to plug in C for everything, so what do I have? It says use the properties of limits, but you know what? Just plug in. What do we got? C to the fourth. C squared, like that. Plus C squared. Minus 1 all over. C squared plus 5. There you go, you're done. Can you imagine how much work you have to do it? Why does this minus 1 stay minus 1 right here? Because, why does that stay minus 1? Because it's the constant rule, right? How come this is C squared? Because the 2 pops out for the exponent rule, and then you have the identity. It's not that bad. Now you know why I leave it out. So if someone's going to be like, well, why is that? You're like, well, that's when someone's like, I don't even understand this. You're just like, just let me take that. I don't usually do this, but yeah, you know it. You know it. So why don't you guys, okay, and I skipped ahead to this because I wanted to save time. Substitution, you see where these x's are? All we're going to do is plug a C in for those x's. That's all it is. And that makes life very easy. That makes life very easy, okay? So, let's actually use numbers now. What do you say instead of a C? Why don't you guys try and figure this one out? I'll give you 1 minute. I'm going to record. Okay, in unison, what do we get? Not everybody at once. 1, 2, 3. 3. Because when we throw a 2 in for every x, we got 2 squared. Plus 2 times 2 plus 4 over 2 plus 2. That's 4 plus 4 plus 4, which we lovingly call 12. Over 4. And 12 divided by 4. My God, you guys are brilliant. And that's how I'm going to end this.